I want to welcome you to my lecture today. Of course, let me tell you what we're basically going to go over this week. We're going to go over spline regression and principal component analysis, then midterm one practice questions. So I know I promise before the midterm one, I'm actually going to go over midterm one practice questions where I'm basically going to tell everyone like what are the areas, that will be covered in the midterm one, along with the other information. So because of that, there's not going to be, there's possibility, you've not received new assignment, right? So I'm considering, since we are very close to midterm, there's not going to be assignments in the week of midterm, so that for you to be able to concentrate fully. And information about practical assignment will be released today, because I now believe that we've done a lot and we can now go practical this time around. Okay, so I want to welcome you to today's topic. Statistics is like a story that goes on and on and on. Today's topic, we focus on spline regression. And of course, in the outline, we're going to consider regression with spline, where we also going to talk about the linear spline, the cubic spline, then the application. Okay, so we want to talk about spline or regression. Of course, the approach we've been using before on estimating parameters in regression model, the approach has been parametric. We'll be using parametric approach. But this time around, the spline regression is a non-parametric regression approach. Now, the advantage of this using spline regression is more or less like, when we fit higher order polynomial. Of course, the more we go in the order of polynomial, you're basically going to see that R square is going to be getting high, telling you the model is actually of high quality. And of course, I told you the other time, the problem we basically going to face where we continue to increase the order of polynomial, we're actually going to run into a problem of overfitness. Now, if we decide not to fit higher order polynomial, okay, we want to fit a lower order, but the only thing we're going to do is that we're actually going to split our data set. Initially we've been using the whole data set, but we basically want to see, in splitting the data set, maybe from one period to another period, the relationship is not going to be the same. That is the idea of spline regression. And that was why I said the technique divides the data set into bins at intervals. Why are we doing that at interval? Because we believe that probably for one period to one period, the relationship may be linear. From another period to another period, it could be not linear, So that is what we mean. And we actually call, that point naught, and each bin has its own separate fit. Okay, so on the other hand, we also have what we call the cubic regression spline, that we call a generalized linear model in a regression analysis. But you know what? I'm basically going to focus on the spline regression. So what is the motivation of using spline regression? The motivation for using that, there's one thing in statistics, the moment there's a problem with one, we actually want to have a way out. Okay, we have a problem with polynomial regression, because the more we increase the order of the polynomial regression, the better the quality, but the better the quality only in terms of bias, not in terms of variance. Because when you consider a lot of variables in your model, even though you are solving the problem of bias, of reducing bias, but you are, you are also creating another problem of the high variance. And high variance will lead to overfitness. It means your model will lead to overfitness. And that was why I said, in order to overcome the disadvantages of polynomial regression, okay, we can use an improved regression technique in the name of spline regression. So instead of, in the polynomial regression, we were only building one model for the entire data. But in the case of spline regression, we're not going to do that, because we're actually going to divide a set of data. But how do we divide, data set into bins? Okay, I'm actually going to walk you through that now here in this course, or in this particular lecture. Okay, so now I'm going to show you the way it is. If you look at the first one, it means your data set, the entire data set, has already been categorized, where you're going to say, okay, when S is less than a C1, you're actually going to have a threshold. There's going to be so many thresholds. You're only going to have one threshold when you divide your data set into two parts. But dividing your data set at time into two parts may not be good enough to be able to overcome that problem associated with the polynomial regression. So what I'm actually showing you on the board now is trying to show you the numbers of categories, the data can be splitted into. So we call that a piecewise step functions. Okay, instead of us to fit the same model for the entire data, we want to believe that we have to split the data into different bins. And, we basically, there's possibility of fitting the same, different model for, different bins. But you basically going to see. Now, I'm going to start with this. I told you the other time when we're working with the polynomial regression, the only condition under which you're going to consider polynomial of order 3 in your model is when you have a reason outside your data. I'm going to say that again. The only condition under which you can tolerate or you're going to consider cubic form of polynomial is when you have a reason outside your data. Okay, so now I want you to take a look at, let's say, for instance, we've considered polynomial regression, even though this polynomial regression of order 3 may solve the problem of bias, but may have a little bit of high variance. But instead of us to we want to increase more, maybe instead of us to say, okay, let me consider polynomial of order 4 or order 5, instead of us to do that, spline idea can be used, where I'm only going to use polynomial of order 3. I don't need to consider higher order polynomial. What higher order polynomial will actually give me is what that spline is going to give me when I only focus on this same order. But if you take a look at the assumptions that I'm giving to you on the board, I'm giving you the idea of a one threshold C, where I'm trying to partition the data set into two. One part, I'm going to fit polynomial regression of order 3. The other part, I'm going to fit the same polynomial regression of order 3. But let me tell you this, there are some data set where we are not likely going to fit the same polynomial of order 3. But based on what I just saw, what I'm projecting now, let me tell you the reason why I'm doing what I'm doing now. I don't want to go over the polynomial of order 3. because I know the highest order that makes sense. If we want to go the far we can go, that is reasonable, in the order should be order 3. We shouldn't go beyond that. Even though I told you the only way to tolerate order 3 in your model is when you have a reason that is beyond your data. I told you nobody goes into research with an empty mind. You've reviewed the literature, you know the relationship, and you basically the essence of fitting statistical model is just for you to be able to confirm whether what you have in mind is what is happening or not. Now I'm going to repeat what I just said again. Let's say, for instance, you have a model, a polynomial of order 3. Maybe that is the best model you have now. And if you want to improve on this model, you may be tempted to go for higher degree of polynomial, but higher degree of polynomial is going to cause a problem, even though you're actually going to reduce bias, but it's going to the variance will be very high. And what will happen when the variance of a model is high, will happen over fitness. We don't want to run into that. And I'm now giving you the idea of, okay, split your data. Instead of increasing the order of polynomial, split your data into 2 at least and fit the same order of polynomial. And C here is basically going to be a threshold. But let me tell you this. Let's assume that what I have here is my data set. And I basically, what we normally do, the very first preliminary investigation is to draw a diagram, like could be a scatter plot, right? Now, look at what I'm trying to see. I basically, of course, looking at this data set, looking at what you are seeing in terms of the bars, you're basically going to be thinking that the idea of a continuous, using the higher order polynomial may not even work. You are seeing some possibility of heterogeneous in terms of the behavior. If from one hand, look at the way it's going, from the other hand, look at the way it's going. Okay, if you join that together, you're going to look at it in another realm, you're going to see this, or you're basically going to see this. Look at that. If you want to look at from the other side, that situation like gets stabilized in a way. Look at that. Initially, look at the way it is. Okay, so to tell you that the idea of a spleen is needed in this kind of situation. Okay, now I want to start with the linear spleen. How does the linear spleen different from, the ordinary linear regression? The ordinary linear regression, where we basically have a mean function. You know the mean function that I showed you the other time. We're talking about multiple linear regression, right? Where you basically going to have, like we're talking about linear regression, y equal to beta naught plus beta 1x. This is a simple linear regression, right? If I want to introduce a linear beam, I can have it that way. I'm for first half my model, and the next that I'm actually going to be having is just going to be subtracting a1 from x, a2 from x, where a1, a2 up to ak may be the threshold. This is an example of a linear spleen. Let me tell you, when we're talking about spleen, okay, we can actually start from linear spleen before we go into quadratic spleen, or we go into the cubic one. The one I show you here, okay, the one I show you here is like, this is not a linear spleen, where I'm actually telling you, okay, fit polynomial of order 3 to this, maybe from this point to this point, and upper, beyond that point, also fit the polynomial of order 3. Now, okay, now, what about the cubic? What about the cubic one, the cubic spleen? The other time, there's something I want you to see. Extension of a simple linear regression is a linear spleen. Look at that. After beta naught plus beta 1, that's what you see. You saw that, right? Now, let us now write the quadratic spleen let's write the polynomial spleen and let's see how it's going to be. For instance, if I want to talk about polynomial of order 3, right? Or now from the polynomial, the extension of the polynomial of order 3 is the cubic spleen. So I'll first write the model that we know, beta naught plus beta 1s plus beta 2s squared plus beta 3x3. The next thing I'm going to do, I will start subtracting the A1, the A2. Now I needed to take a look at this and look at this. You're basically going to see that the spleen that we're talking about in terms of model specification is just an extension of the conventional one. Okay, now go ahead, go ahead. We have a B4, we have a B5. The BK plus 3 is more or less like, maybe I get to the middle before I get to the last. Maybe I'm going to you're going to be going like that and stop at a middle. It's just like to tell you that it doesn't end here. We also have some time. That was why I put plus that we still have. Does that make sense? Okay, this is what happened. I actually put plus k plus 3, that x minus k raised to power 3. Like if I'm talking about cubic now, I will stop at raised to power 3. Okay, now if you take a look at, let me show you this. But let me tell you this: when you cut your data set into, when you use so many piecewise, and maybe it does not require you using so many piecewise, then you're actually going to run into the same problem that you are running away from. What are you running away from? You don't want to go higher order, all right? So the same problem that you also go to run, that you want to prevent yourself running into, you may run into that when you have a lot of spleens, but we have a way to optimally determine the numbers of spleens. Does that make sense? Okay, now, of course, we also reduce residual sum of squared. I told you the other time, the residual sum of squared in a conventional linear regression, right? We want to reduce the error, right? Now, even in the spleen, we also want to reduce the error. Therefore, there's going to be, if you take a look at what we are adding lambda integral the g prime prime t squared. It means that lambda, there's going to be a penalty. Does that make sense? So I'm going to explain all this to you, but what I'm just trying to say is that we know introducing spleen, we basically add something to the sum of square, but the variance of the model will be reduced. Okay, the variance of the model will be reduced, even though the bias may go up a little bit. I told you the other time, we cannot solve the problem completely. When you solve the problem of reducing bias, then you have caused a problem of increasing variance. When you solve a problem of increasing variance, maybe you reduce variance. When you reduce variance, then you increase bias. We know that. But if we can have a trade-off, that is why you have the lambda, a trade-off between the bias and the variance. But I know by the time you get to application, you really understand more. Now, take a look at this. The piecewise cubic will look like that. I'm looking at the effect of age on the effect of age on the wages. Okay, and I make a plot. The very first thing you always do is to do what? To generate a scatter plot, right? Now, we need to pay more attention to the scatter plot. Let's look at number one, where we're talking about, look at what happened at after 50, age 50. The relationship age has with wage from 0 to 50, up to 50 is different from the relationship that is showing. I'm going to show you. Anytime we see that, we're basically going to call that a piecewise cubic. Anytime you see the other one, that's a continuous one because there's no cutoff. The first one, there's a cutoff. But look at the other one that keep going, right? That is what we call continuous piecewise cubic. What about cubic spline? Okay, this is the one you are seeing now is a cubic spline. The other one is a linear spline. Look at the linear. You see like that straight line and it just go. So what am I trying to show you here? What if you plot your data and you basically want to figure out what kind of spleen are we talking about? But you know what? In this course, because if I want to go more into this, it's going to be beyond this course, beyond the level of this course. But which one do we want to focus on? If I'm going to bring out anything in exam, it's basically going to be the one that I want to show you now in application. Okay, but we just needed to have this as information. Now take a look at this. You have a data set on deals and sales. Okay, day 5 you sell 100, day 10, okay, you can see that, right? Now your 404 cell generates your scatter plot. Don't forget, when you generate your scatter plot, this is what you have. Do you know this is going to suggest to you you should split? Look at that. If you want to split, can somebody tell me where it is reasonable to split? Where do you think it's going to serve as a threshold? Yeah, where? Exactly. Good job. Send me a message for extra credit at that very peak. I wanted to take a look at that. You know, when you take a look at this, the idea of splitting is going to work. Okay, now, if I decided I don't want to go by applying a spleen, and I start with the simplest form of a model, linear regression. You know, linear regression, I'm just going to do sales on day, right? Let's just say I just want to use linear. I'm not interested in spelling. I only just want to show you the error that you're going to commit. Like if I'm supposed to go for appropriate or the best of, and I settle for the one that is not appropriate, what penalty am I going to say? I mean, what penalty am I going to suffer? The penalty you're going to suffer will come in terms of increasing your residual sum of square. Now, when I do that, I want you to pay attention to the R squared. What happened to the R squared, you know, when you only use linear regression, sales on day, you know, particularly when you are working with a time series data, the behavior in some period may be different. The behavior of sales in some period may be different from the behavior in another period. Now, if you take a look at the multiple R square here, if you want to look at the contribution of Dale to sales, what happened? 39.53%. That's not good at all, right? Okay. Now, you know, which means, what am I assuming if I use a straight line? When you draw a straight line, can you reasonably say the straight line captured that? No, far from it. Far from it. And you can see that from the R square, right? Now, what do you think would be the next thing I'm going to do? The next thing I'm going to do is to consider the second order polynomial, right? You know, the linear regression is the first order polynomial. Why do you think I'm actually considering the second order polynomial? I'm considering the second order polynomial because I see a curve, but it is not every curve that the second order polynomial can capture. You know that, right? Okay, now I know that the linear regression fail, which is a polynomial of order 1. Now I want to consider the second order polynomial. Now let us see what happened when we fit the second order polynomial. When we fit the second order polynomial, we actually what is the R square now? 90, which means the second order polynomial is basically doing a great job. But there's something I wanted to take note. In the second order polynomial, you're going to see that where you have day, you can see any, right? There's no way you'll be able to actually, if you want to take a decision regarding that. Okay, now, do you know I can now bring the idea of a spleen in now, where I need a threshold, and somebody just suggests to me that, oh, why not taking the peak to be the threshold? Now, and that very peak corresponds to 90. If you want to check, that peak that guy mentioned the other time corresponds to 90, Okay, so now because of that, I said, in case of a spline regression, we divide that set into two bins, okay? For our case, let us divide that set into two bins so that, let's say around day 90, of course, I'm using the peak. So one of the left side of the peak that they occur is basically going to be equal to 90, right? And the other, the right is basically going to. So now I'm actually going to split that data into two. Oh my God, this is what I have now. Do you see that? I just broke that into two. Look at that. Okay, so as you can see now, that has been broken. I use the threshold 90 to break that into two. Now, how do we now program this in R? You don't need any sophisticated knowledge of R to do this. Now, of course, what are we assuming now? We basically want to assume a linear spleen, right? I'm going to take you back to when I was displaying some stuff to you the other time. You see linear spleen, right? Okay, you can see a kind of straight line stuff. And if you take a look at this guy here, okay, when you put a straight line on one and put a straight line on the other one, you basically, this is what you're actually gonna. Okay, I mean, before that, you're actually gonna have this. But why is it that quadratic does not automatically capture that? Let's see. What do you expect in quadratic? You expect a curve, right? Whether concave up or concave down, right? Now, does the quadratic capture all those? There's some 3 points that I'm seeing outside the curve. Oh, do you see that? Does that line or curve cover them? No, it doesn't cover them. Even though quadratic has an improvement on the linear, but I don't think it has taken us to the destination. We basically need an approach, that will take us to the destination. And that is why the idea of a spline is coming in. So in case you plot your data, some of you, you work with data most of the time, and you see something like that, instead of you to just go with one particular method, why can't you try idea of a spline? Okay, and testing the idea of a spline. Of course, don't forget the peak could actually going to serve as the threshold. Okay, now I said something here. I said we can see that it is not a bad fit. Like, this guy is not a bad fit, but not a great, not a great one either, not a great one either. And I said polynomial regression also comes with various disadvantages that it tend to overfit. I told you the other time. Okay, and it may lead to increase in complexity. Okay, or as the number of features increases. So the disadvantages of the polynomial regression can be overcome using the regression spleen. Because when I see this, without regression spleen, you know what I'm going to be thinking? I'm going to be thinking increasing the order of the polynomial. When I increase the order of the polynomial, that could lead to overfitness, even though the bias is being reduced. It's not only bias that we want to reduce in statistical analysis, we also want to, bring down the variance. Okay, so idea of the spleen, we're going to use that now. Okay, we have a way to investigate whether intervention work. Now let's see. I want to code now. I want you to pay attention to this code. It's very, very easy. It's only, since I'm having like, we're actually partitioning our data set of data into two. I'm actually going to use that IFELSE for categorization. Then I'm going to say data $day greater than 90, 10. Why do I have 1 and 0? 1 and 0, maybe 1 is maybe situation where it is greater than 90, and 0 situation where value is less than 90. Okay, so then I need the data $different, which is just going to be, I'm going to be saying minus 90. You see that? That data minus 90. Okay. And why am I saying data minus 90? Don't forget the other time I show you S minus A. You see in the, why do I say data day minus 90? I wanted to go back into what I started showing you from the beginning. Do you see what I was showing you from the beginning? Okay. But this one, the one I'm showing you is just general. We have so many spleen knots, but the example I'm treating now is just one knot, which is 90, threshold 90. Okay, so that was why we were doing that. So I'm gonna go back to the code now. Okay, so minus 90. Okay, now this code here, this is what I'm doing. Let's go back to the data. The data start with 2 columns, right? Day and sales. Okay, now the next thing is, why do I have 0, 0, 0, 0? Where I have 0, 0, 0 is where that particular say is less than 90. Look at that. Do you see that now? Less or equal to 90. Do you see that? 0, 0, 0, all the way to data point number 7. Do you see data point number 7? What was the sales? 90, right? We're going to code that as 0. Don't forget, you are splitting into 2. The idea of 0 and 1 will come in. Labeling, right? Okay. Well, from data point 8 to data point 13. Okay. So why do we have 111? Because 100, 110, is actually greater than 90. So here I'm actually using days, I'm categorizing days, not sales. And the threshold is 90. Okay, any day that is less or equal to 90 will be coded as 0, and any day that is greater than 90 will be coded as 1. Now, what do we have at the other hand? That difference, how do I get negative 85? It's 5 minus 90. That was what I was coding here. Do you see that? The data $day minus 90. Do you see that? So that minus 90, okay, 10 minus 90, that will be minus 80, right? 25 minus, do you understand the difference now, right? Okay, now, the moment you now have the difference now, so the next thing is basically going to be X. If you take a look at what we have here, you see the way we want to derive the data sign X, which is going to be what we got there, right? Multiplied by the data X bar. Do you see the data X bar? Okay, so I want you to take a look at this guy now. Okay, how do you get 0, 0, 0 until you get to, how do you get 10, 20? Now take a look at that. Do you understand that now? How we got how? Now that we got this, then we can now go into, can apply. Now look at the new code now. I'm going to say sales. Okay, data plus X. Okay, I mean day plus X. Okay, now the day and the x, day is 5, x equal to 0, day is 10, x equals, if you take a look at that now, so I'm putting that into consideration. So that is what I pull here. And when I did that, this is the result of spline, linear spline. And I needed to look at the R square. There's nothing like NA in this table. Look at the R square. What happened? The R square, we're able, imagine that. People don't really believe that we can increase the R square without increasing the order of the polynomial. Is that not interesting? We did not increase the order of the polynomial. We did not even fit the original order 2. We fitted under 1, except that the data set was partitioned into 2. And what was the R square? 95.92%, compared to when you fit, and here there is not going to be any problem of mathematics of a complexity. There's not going to be any problem of increased variance. Okay, so take a look at that. Any question? So which means this guy now, compared to fitting quadratic, just fitting this guy, compared to fitting this guy, that guy is better than this guy. But before we started considering spline, the only thing people they're going to think about is maybe I should increase the order of the polynomial. So don't increase the order of the polynomial more. I mean, again, that's what I'm telling you now. If there's a violations of linearity and stuff like that, you also need to check whether the idea of the spline can work. But you know what? In this particular data set now, one threshold, one knot up out. If I use 2 knots, more than 1 knot here, then I'm going to run into issue. I shouldn't waste the numbers of, when there's no divisions, why am I creating divisions? If I can classify the entire data set into 2, why do I need to classify further? Because you can actually see from, you can see from there, you can actually see from here. Okay. And I also want to tell you, you don't expect or even if you look at the first, if you look at the day data, okay, the first day data, you don't expect all the points to be on a straight line. That's why it is called scatter plots. When all the points are on the straight line in both, you know what happened? Then you are no longer using statistical model. It means there's no error component in your model anymore. It means you are now using a model that will capture exact reality. We don't have that in statistics. And I want to believe we don't have that in the world. There's always going to be a room for error. And that's why you don't expect all the points to be on the same, to all of them to land on the line, which is going to be a perfect relationship. But the fact, if the points are not far away from the line, we're fine. Okay, so based on that now, this is exactly what we are now having. If we now want to put a line, okay, putting into consideration the spline that we've done. Yeah, go ahead. Can you say that again? Oh no. What I actually said is this: if you fit a simple linear regression, we normally start with the most simplest form of the model, right? Why do I need to go for the higher model? Maybe that was a violation. We saw a violation the other time. You can remember when we fitted simple linear regression. Yeah. When we fitted simple linear regression, we actually saw that, of course, there's a violation here. And the next thing that will come into our mind is, let me go for polynomial regression, right? Because I'm seeing something that look like a curve. That was why we go for this guy here, right? And when we go for this guy here, when we take a look at this, we realize that we have some points that are not covered by that curve, and If you have that point, the next thing that will come to mind, why can't I go for the higher order? But we know the consequence of going for the higher order polynomial, that it may lead to overfitness. That was why we are running away from the higher order. So the spline regression should be considered in a situation where you want to overcome the disadvantage of the polynomial regression. You don't want to go higher order, because when you go higher order, the more order you go in the polynomial, the more the complexity it becomes, and not only that, the variance is going to be increased. When the variance goes up, you know what happens? Overfitness. And the meaning of overfitness is that your model will perform better on the training, but it's performed poorly on the test data, on the unseen data. Go ahead. Oh, it can overfit. Oh, I get your question now. The only condition under which spleen can overfit, there are so many conditions. Number one, where you're supposed to use one knot, like one threshold, you use more than that, then it could overfit because you've wasted that knot. So that was why I was trying to say, you notice that there are so many divisions in the data. That's why you now want to introduce a lot of knots. In that situation, it will overfit. So we should be guided on how to split our data set. Like somebody suggested to me the other time that, oh, looking at this data, looking at the relationship now, this can be splitted into two using the peak, which really makes sense. So, I noticed something in this world. Anything that has advantages, we also have disadvantages. Don't use the optimal numbers of knots when it comes to spleen. And when you use so many knots where you are not supposed to, then overfitness will also, which means the problem you are running away from increasing the order of the polynomial, you now cause that problem again, or you fall into the trap of the problem again. So that's a good question. So now, finally, we now have this, which really makes sense. Okay, we've splitted the data, into two, but I'm not going to go beyond this in this class, because spline regression, there's a lot, that goes with that. But I'm just giving you this as an information. You know why? We've already done polynomial regression, and you will notice that the more you increase the order of polynomial, the better the R square. But the fact that R square is increasing does not mean the effort is making sense. The effort is only making sense in terms of what? The effort is making sense in terms of reducing bias, because reducing bias means, how can I reduce bias? The more time I put in the model, then the less will be the bias. But that is not going to be good for somebody who want to make prediction. I told you the other time, in statistics, you need to choose whether do you want to explain or you want to predict. If you want to predict, then if you go by way of increasing the order of polynomial, okay, then it's basically not going to work because the variance will be high. But the idea of the spleen is, how can we stay in the middle? How can we balance it? Okay, I know that when I try to improve on the bias, the variance will go up. And that was why the other time you saw a penalty in the formula for residual sum of square. You saw that lambda, right? That lambda is something that is checking for over parameterization. Okay, so I wanted to, but like I said, I'm only going to restrict myself to just a linear spleen. Now, somebody can say, okay, on this data, can I use a quadratic spleen? Quadratic spleen is more complex than linear spleen, even though I'm actually going to use one threshold, but it doesn't make sense using quadratic spleen because take a look at what that this is when I was showing you this. I'm gonna go back now. Okay, here. Take a look at that. For that data set, I cannot fit continuous piecewise cubic. No, that is not the shape we saw. But that was the shape we saw, linear spleen. That was why I show you all this before I start. The only thing we've done today in application is a linear spleen, which means when you plot your data and this is what you are seeing, then you cannot go by way of linear spleen. You have to go by way of, we have a cubic spleen, we have a continuous piecewise cubic, we have a piecewise cubic. The only thing you're just going to be targeting is the picture here, because these are more or less the possible ways the data is basically going to be, but it's going to look this way if you're only considering one threshold. You can see in all of that is 50, right? It is a maximum, whether for linear, whether you want to take it for linear or you want to take it for cubic spleen or the other one, we use the threshold of 50. Does that make sense? We could have some data set where the number of threshold will be more than this, but you know what? Arrow is easy now. Arrow has made things easy. Do you know we have a package in Arrow when you just run it, it will optimally determine the optimal numbers of spleens you're gonna have. You don't need to worry about anything. But I'm just showing you this, just like you should be able to know, like for information. Any question? Go ahead. Oh, you mean to consider for the splitting? I think you mentioned an outlier now, right? Oh, you're talking about whether it matters how close to the center it is. You are right. That's another topic in spleen. You are very correct. You know, like I said, do you know this spleen? We can take it as a course where we're going to talk about, okay, what if I want to consider the case of outlier or cluster? What if I want to consider a situation where maybe some are very close to the center or some are far from the center? So we also have that consideration. But the one I've presented today is just like, okay, the simple one where, okay, I'm only going to focus on the peak, okay, to split the data set into two. But just like what you said, there are other considerations. That's a very good question. Do I still have like 5 minutes more? Oh, okay, like one. Look at my eye. Okay, so let me see other thing I'm gonna the I think exam is Monday, right? Did you check when I put the syllabus? What do you see? Is it next week? Oh, is it this Friday? Oh, okay. Now, so it's going to be next Friday. The review is going to be on Friday, this Friday. Okay, which means I'm going to have lecture this Wednesday, right? Another lecture this Wednesday, but Friday is when I'm going to have, you know, the review. Is there any other thing I want to talk about? Let me see. Okay, go ahead. Yeah, I think I want you guys to, no, you don't have practical. I've changed it. I, you know, I don't think so, because I wanted to prepare, like, I know the exam is going to be the upper week, but I'm going to release practical instead of the assignment. For now, I think you've done more than enough assignment. So you need to relax. Okay, make sure you stay safe and have a very beautiful